Hi. So in this episode, we'll discuss the Walrasian demand function further, and we want to assume that those demand functions they're continuous and differentiable. Okay, and we'll also talk about some comparative statics, which are just some properties that we have in the optimal Walrasian demand functions. Okay, so remember that if we have the Walrasian demand correspondence to only include one single value in that set, then we can call this as the demand function instead of a general correspondence. Okay. So if we write this x and expand all those dimensions, so we could have from 1 up to L dimensions. Okay. For all those dimensions of different goods, L goods. Okay. So now we simply assume that this x function, okay, so now this is a, you can regard this x to be some optimal value, but it is also a function, okay? So it will be a function in terms of p and w, okay? So we solve this x from the UMP, right? From the utility maximization problem with regarding this under the constraint of budget. But here, this p and x as a solution, it can be also a function of p and w. Okay, so that's where we're calling this as a function. So now we assume that this x it is differentiable, and of course, if it is differentiable, then it has to be continuous. And now, okay, so now let's fix the price. Okay, so this p bar is still a vector. Okay, so we fix all the prices here. And this x, this function is called angle function. Okay, and you might have heard this before. And sometimes we can also call this path as the wealth expansion path. Okay, so and we call this partial derivative of xl pw with respect to w to the wealth, and this is simply called the wealth effect for the Lth good. Okay, so now we have this picture to illustrate this idea of the wealth effect. So we simply have two goods in this two-dimensional real numbers, positive real numbers, and here we have this all those parallel straight lines segments as the budgets, right? So under all those budgets, we have different level of w's. So here we have w, here we have w prime and w double prime, and where w double prime is the biggest one. Okay, so as the w at the wealth increases, and then we use all those indifference curves, okay, and then which are tangent to those budget sets, and we solve all those black dots, okay, which are the solutions of those x as the functions regarding this fixed price p. I think I missed just a little part here. Okay, fixed p and the change in w's. Okay, and this line or this curve is called the angle function, or this wealth effect. This path. Okay, so and next we want to introduce the idea called normal good. So we say that good L is a normal good at some price p and wealth w if the partial derivative of x with respect to w is not negative, is positive or equal to 0. Okay, and so correspondingly we call some good to be inferior good if this derivative it is less than 0, it is negative. Okay, so and this normal good is easy to understand. So for an inferior good, so if the let's suppose that if the price we're not changing price, if the income or if the wealth increased, then we consume actually less than before. Okay, so that's why we're saying that this good is inferior. Then as we have more money, then we do not want to consume more of those goods. Okay, So that would be the wealth effect. Okay, and now let's introduce another concept called offer curve. Okay, corresponding to the angle curve. So offer curve refers to the case where we fix the income or the wealth W, and we also fix other prices. So we use this negative L to denote all the other prices, okay, except L. So we fix those things, and then this X, in this case, it is called the offer curve. Okay, and correspondingly, this partial derivative of X with respect to this. So this would be the XL, and be careful, but this would be with respect to good K. And this is the price effect of PK on the good L's demand. Okay, so this is sort of a cross effect. Okay, so the price changing price from good K, and we want to have this effect to measure this effect on the good L's demand. Okay, so all right. So if this effect, if the partial derivative of X with respect to P L itself, if this is positive, okay, then we simply call this L good to be a given good. Okay. All right. So now let's have some examples. First is this picture. Okay, so be careful that in this picture we don't have normally the same axis as before, but here we have x2 on the horizontal and p2 on the vertical. Okay, so this picture simply shows the change, simply shows the x2 as a function of p2, and with different levels of p1s. Okay, so for example, here on the bottom curve here is the level or the function of x2 given some p2, and this would be under the price of p1 double prime, and this is under p1 prime, this is under p1. Okay, so next we want to show this offer curve, okay, and with some normal good, so and nothing is inferior here. So we have this point as the point if we have zero consumption x2, and if we consume all the money, all the wealth W, spend all the money W on this good one, then we have this level, this blue dot as the starting point. Okay, as we so we have this P2 bigger than P2 prime, bigger than P2 double prime. Okay, so if we decrease the price from P2 to P2 single prime to P2 double prime, then you can see that if we do not consume x1, then the amount of x2 that we consume becomes more and more, right, as we decrease the price for good 2. So in this case, if we connect all those solutions, all those x's using those indifference curves with the tangent point to get the solutions of those x's, and then we connect all those dots, okay, as well as this. So there might be a lot of other dots. It's just we omit all those budgets and those dots. Okay, so then we connect all those dots, then this gives us this offer curve. So that would be something normal, but however here, as a special case, so here it would be an example where this good 2 is inferior at some point where this would be the given the fixed price P1, but the P2 is where this P2 prime. Okay, so if let's say Y is called inferior, so normally it would be something like this, okay, along this blue. But after this blue dot, when it goes red, the level of x2 it decreased. Okay, so since this P2 prime, it decreases to P2 double prime. Okay, we have this relation here. And equivalently, we can say that W increases in this case. Okay, because the price for x1 it doesn't change. Okay, so in this case, we can observe on this figure that the level of x2 it decreased from this point to this. Okay, so there will be a decrease on the level of x2. So in this case, from this segment of this red, we can see that at those prices and this wealth level, then this good too. In this case, is inferior in this segment. Okay, good. So this will be a special example. So now we have introduced all those concepts, and then we can start to have some comparative statics. So in economics, the comparative statics is normally referring to simply some comparisons of some outcomes. Okay, so those outcomes or economic outcomes, those could be just some equilibrium outcome that we introduced in game theory, or in a supply demand equilibrium that we're gonna introduce later in this course. But this will be, it can be also just some outcome on this optimal solution of this consumption set, right? So any outcome that we can do, and those would be the comparisons of some outcomes as we change some exogenous parameters, okay, such as the prices or the so the exogenous means that the parameters that are given exogenously, okay, so they're given from outside of this model, and we do not take those parameters as some choice variables, okay, such as the prices or the wealth here in this case. Okay, so good. Now we can have our first proposition that will be on the textbook, which is 2.8.1. So we say that if a Walrasian demand function is homogeneous of degree 0, and then for all the price and wealth, then we have this equality here, okay, which is the summation of all the partial derivative of x with respect to p, pk, and multiplied by the pk itself, and plus the similar term, the partial derivative of xl with respect to w, and multiplied by w, and those two, we sum those two together, and this has to be 0. So the proof will be very simple. Okay, so if there is a homogeneity of degree 0 and for any alpha with a positive number, and we simply have this as a definition of homogeneity of degree 0, right? So we simply multiply, we can multiply any positive number in front of p and w, and this doesn't change the solution x. Okay, so remember that this is still in a vector shape of vectors, right? So actually we have all those alpha p1, alpha p2, alpha pl inside of this bracket. Okay, so now we can take the partial derivative, and with respect to alpha on both sides of this equation, of this homogeneity of degree 0, this equation. And then we can use the chain rule in the derivatives, and then expand all those terms. Okay, so the first derivative that we can get is to simply to take this x l with respect to, because this we want to take the partial derivative with respect to alpha. Okay, so this will be important. So which terms contain the alpha here? So we can see all those terms, they have alpha inside. Okay, so we first need to take the partial derivative of xl with respect to this, all those terms. Okay, alpha p1, alpha p2, alpha pl. Okay, and even alpha w, right? And then next, what we're going to do is to take, using the chain rule, to take another derivative of alpha p1 with respect to alpha, and then we can get the partial derivative of with respect to alpha for each term, and then we sum all those terms. And here, similarly, we have this in the term of alpha w, right? Okay, then this is 0. So now we simply set alpha to be 1, okay, and then we can further simplify this to the following, and which is just the result that we're gonna prove, that we just wanted to prove. Okay, good. So how about the intuition or implications of this result? So this homogeneity of degree 0, it implies that the price and the wealth derivatives of demand for any good L, so if we weight those by the corresponding prices and W, and this has to sum to 0. And intuitively, this is simply because the price and wealth, they increase proportionally. Okay, and its variable just changes in proportion to its initial level. Okay, good. So And alternatively, we can also write this in terms of the elasticity of demand. So we might have seen this before, right? So elasticity of demand and with respect to P and W respectively. Okay, so the first concept or the first elasticity that we're going to define is this elasticity of demand with respect to the price of good K. Okay, so here we have the change of XL, and this is a percentage change, and over the change of price, but this is the price of good K. Okay, so be careful. And then we can rearrange those fractions, and this change of XL over change of PK, this is simply the partial derivative of XL with respect to XK, to PK. Okay. All right, and similarly, we can define the elasticity of the demand with respect to W. Okay, and we have the similar definition as before. Okay, then we can rewrite the above result that we obtained previously and use the elasticities to simply write this as follows. Okay, but it will still have the similar meaning, but you could also try to interpret this in terms of elasticities. Okay, good. So next, some other comparative statics that we're going to have is regarding the Walras's law. Okay, so now the previous one was about the homogeneity of degree zero, right? So now if we assume that the function, the Walrasian demand function x bw, it satisfies the Walras's law. Okay, so remember that the Walras's law simply refers to the case where we spend all the money. Okay, and then for all the p and w's, then this proposition says that we have this relationship. Okay, and this looks very similar to the one before. And then again, we're gonna use the partial derivatives to obtain this result. Okay, so how do we do that? So recall that in Walras's law, we spend all the money, so it simply means that the price times the demand x itself. This has to be binding to this equal to this wealth level. Okay, so this has to be binding, and it cannot be less than W. So, and in this is still in the vector, and if we expand all those terms inside, and this is as follows, and then we can simply take the partial derivative with respect to the pk on the two sides, and this simply gives us this and plus this term. Okay, and that is essentially the one that we're going to we need to prove. So this is called the Cournot aggregation. Okay, and similarly, in using the same conditions as above, if x also satisfies if x satisfies this Walras's law, and then we have something regarding to the wealth. Okay, and this on the right hand side, this is y now. Okay, so similarly, we just use the Walras's law and take the partial derivative with respect to w on the two sides, and this would simply gives us this result. Okay, and normally we call this as angle aggregation. And you can see that angle normally it relates to the wealth. Okay, good. So let's have some interpretations of those results. So those two, they're just some differentiable or differential version of two facts. Okay, so the first is that the total expenditure cannot change in response to a change in price. Okay, so we have this zero, so this cannot change in response to a change of price. Okay, and the second is that the total expenditure, this has to change, or it must change by an amount or the same amount equal to any wealth change. Okay, so this change has to be the same, so that this right hand side equals to 1. Okay, so good. So now we have a lot of very useful comparative statics, or just some properties that we have if the x, this function, satisfies the homogeneity of degree 0 or Walras law, then we can derive all those interesting properties. Okay, good.